So we talked about various ways to solve first order differential equations analytically. We talked about separable equations, we talked about linear equations, and we talked about exact equations. And another method is basically to change the variables, okay, to change the variables to make the differential equation easier to solve. And these various methods are grouped together as substitutions. So, just to be formal here, what is a substitution? A substitution is a relation. Y is equal to gxy. So here, you're substituting for y some relation, relation of x and u, some function of x and u, where u is considered a function of x. Okay, so u becomes the dependent variable instead of y. But you could still have x in there in the substitution. Okay, so we'll solve for y instead of we'll solve for u instead of y, and then ultimately solve for y by substituting back. So that's used to transform the first order differential equation that we see here. Okay. So by the chain rule, and again, u is seen to depend on x, okay? So if we take the derivative of y, and we have this expression g of xu, then the chain rule gives this, okay? That's just a chain rule with multiple variables, okay? And here we'll just get dx once we take the chain rule. That's just one. But u does depend on x, so we keep that. And so now we have an expression for dy dx. And so substituting for dy dx this expression that we just found here, so taking this and putting it here for dy dx, we have this relation. And notice instead of y, which we had y over here, instead of y, we'll substitute our substitution, right? We'll get the relation and plug it in wherever we see a y. We'll plug in gxu, whatever that is, okay? And solving then for du dx, just to put it in normal form that we see here, with instead of dy dx, we have du dx, we'll get this, okay? And now the basic idea here is that this will be easier to solve than this, okay? So we have a new dependent variable u and the same independent variable x. If u equals phi x is a solution to this differential equation, to the transformed one we call it, then y equals gx, and wherever we see a u, we substitute phi x, the solution, in. And so notice that this will just depend on x now. Okay, so we'll get y in terms of x, and it'll be the solution to the original differential equation. So this idea is just substituting back. Okay, and so that's the general idea of substitutions, and let's look at specific types of substitutions, and these are going to be for homogeneous equations. Okay, what is a homogeneous equation? Well, first let's define a homogeneous function. A function f of xy is a homogeneous function of degree alpha if f tx ty is equal to t alpha fxy. Okay, so somehow you could like almost factor out a t if you want to think about it that way, and you pay the cost of an alpha. Okay, it's degree alpha. So let's look at some examples. We have fxy is equal to x cubed plus y cubed. That is a homogeneous function of degree 3. Why? Well, Wherever we see a x, we plug in tx, and wherever we see a y, we plug in ty, as we're doing here. And we could factor out that t cubed, and we'll be left with, this was just the original fxy. And so we have this relation here, which conforms to the definition with alpha equals 3. Okay, so this is of degree 3. This here is not a homogeneous function. So, I mean, it looks similar to this, except you have a plus 1. I mean, if you've got t cubed plus 1 there, you can't. So if we had, for example, it's similar to the previous problem, except we would get t cubed x cubed plus y cubed plus 1. Okay? Now, we can't factor that t cubed. If we wanted to further factor a t cubed out of the whole expression, then we'll get x cubed plus y cubed plus 1 over t. Okay? And that is not equal to fxy. Okay? That is not equal to that. So, does not equal. So we can't, so that's why that's not a homogeneous function. This is a homogeneous function here of degree 0. Because notice you could factor out a t from top and bottom. They cancel, you get 1. Well, 1 is t to the power 0. Okay, so it is a homogeneous function of degree 0. We could also have negative degrees. Okay, so for example, this here is a homogeneous function of degree -1. You factor out that t, you'll get a t squared, square root, you get 1 over t, and there goes the original function. Or we could write 1 over t as t to the -1, and we get this expression, which means that we have a homogeneous function of degree alpha. So another definition here. So we talked about what a homogeneous function is. What's a homogeneous equation? A first-order differential equation written in differential form that we see here is said to be a homogeneous equation if the coefficient functions m and n are homogeneous functions of the same degree. And notice here, like I emphasize, they have to be the same degree. So in other words, this mtxty would equal t alpha mxy, and ntxt alpha ty is equal to t alpha nxy. It's important that these alphas are the same. They got to be the same. Okay? So both of these have to be satisfied for the same alpha for us to say that it's a homogeneous equation. So something to note, what is it about these homogeneous equations? Well, they depend only on the ratio of x over y. Okay, so the differential equation, even though it has both x and y in the expression, what it really ultimately depends on is their ratio. Okay? In some sense, it has 1 degree of freedom rather than 2, right? In general, x and y can be anything. But this equation doesn't care what x and y are in absolute sense, only in a relative sense. And we could see that. So if we choose t is equal to 1 over x, well, in general, we have dy dx is equal to. So if we just rewrite this equation here, this homogeneous equation, if we just move things to the other side, we'll get a negative m over n. And we multiply by 1, and 1 is also equal to t alpha over t alpha, right? So you could cancel that, that's 1. So that's how I inserted that in there. And why did I do that? So I could then, because they're homogeneous functions, factor them into the, and here we're using the word factor in loosely, or distribute n loosely, into the inputs of the functions. So we get that. And let's choose t equals 1 over x. If we do that, these x's will cancel, and you'll have m1 over y over x and n1 over y over x. What does this mean? This means that, if we have some function mxy, then wherever we see an x, we just put 1. Literally just put 1. And wherever we see a y, instead we put y over x. Now we could define a new variable, u is equal to y over x. Okay, and so these homogeneous equations really only depend on u. Okay, you could see this negative m over n as just some function of u. Any x dependence in absolute sense was, we just put a 1 wherever we saw x, and now u is just the ratio. Okay, and you probably guessed that this is precisely the substitution that we want to make here. Okay, that y is equal to ux, and we take the derivative or differential here. And when you take differentials, you do it just like derivatives. You could pretend like there's a dy dt if you wish, and to do this using the chain rule. But so we're going to just take the product. So dy, we just act with a derivative on u times x, and then act on u times dx. Okay, so that's just the product rule there. The d, switched between u and x because they're a product. And we then we then substitute dy into the homogeneous equation, right? So we have m dx and then n times dy. So this is just dy here, okay? We substituted for that, and we then are left with this expression here, okay? This was similar to what we did above with finding du dx, in a sense. And so, okay, this is now, once we add terms that have a factor dx and factor out the dx, and there's only one term that has a du, x du times n, so that's what you're seeing there. Okay, we now have this transformed differential equation, and we could divide by x and divide by mun, okay? And why would we do that? Well, now we have, this is now separable, okay? We have a dx over x term and a n du m plus un term, okay? And so this only depends on u, this only depends on x. This is separable, okay? We could solve separable equations. Now, we saw that only the ratio matters. So we could have, instead of setting y equal to ux, we could have set x equal to vy, okay? Instead of u, we now have a v, just to distinguish from before. And if we follow the exact same steps, this time we have dx is equal to dvy plus dyv, okay? We end up with this separable equation, okay? And so now we have dy instead of dx. So we could have gone that route. There's nothing, there's nothing that would have prevented us from doing that. And if we let fu equal negative m over n with the transformed variable, okay, then we would have this difference. So this is equivalent to this, okay? So you could see that by playing around with these and, factoring out an n. If you factor out an n from the denominator, it would cancel and you would get an m over n. And, you could sort of play around with that. And we basically have this transformed differential equation there that we could solve. So let's look at an example. We want to solve this. First, note that it is indeed homogeneous of degree 2. You can check that readily by doing what we've done above, and you see the t squared there in the original functions. So, okay, this differential equation is homogeneous. We're going to choose this substitution. You know, we could have just used this formula too, like that we derived, and just, you know, we would take n, for example, you know, n over there. Well, we have an n, and we would plug in, for x, we'd plug in 1, and for y, we'd plug in u, where u stands for y over x. But let's just go through these steps again, okay? I'm not sure it would be helpful to just memorize these. You usually actually get easier expressions if you follow through with each example than using the formula. So, okay, we take the derivative, we act on the differential, which is just the product rule there. And we plug, for dy, we plug that in here, and we end up with this expression for dy. And this is important, okay? We had x squared plus y squared. You got to substitute ux wherever you see a y. Okay, so we should be left with nothing but u and x there. And we are. So you substitute for two things, for dy and for y itself, okay? And, you know, simplifying and gathering terms, so you have a dx and du factor, we get this equation here. And now we could divide by 1 plus u and divide by x cubed. So we divide by those two to end up with terms like this. And now we could just integrate. How do you integrate 1 minus u, 1 plus u? Well, you just use long division here, okay? And you end up with this right here. And you integrate 1 over x, and you end up with this expression. And then just simplifying, okay? We leave a c1 here so we could write a c at the end. And just going through the straightforward algebra, you end up with this expression here, which is an implicit solution, okay? You can't solve for y explicitly there, okay? But we just solved this differential equation. If this was an IVP, we could fix c, but it's not an initial value problem. So substitutions vary, right? There are various types of substitutions we saw above for homogeneous equations, how to work with them. And there is a special type of substitution for Bernoulli's equation, okay? Bernoulli's equation looks almost linear except for this y to the n there, where n could be any real number. So equations of this form are called Bernoulli's equation. And you probably guessed how we'd want to substitute, what kind of substitution we'd choose, right? We're going to choose a substitution that would transform this to a linear equation, okay? If we choose the substitution here, okay, or in other words, y is equal to the 1 minus n root of u, okay, then du dx, again, be careful, you have to use the chain rule. You take the derivative of the outside function, the 1 minus n drops, 1 minus n minus 1 is going to be negative n, and you have dy dx there. Solve for dy dx, and you end up with this expression here. Now take this for dy dx and plug it into that, and so you have this here plus pxy, f of x, y, n, and you could probably see what's going to happen. okay? We need to have everything just in terms of u, okay? And we have these y's there, but if you multiply by y to the negative n, this y would cancel. You get y over yn, okay, multiplied by y to the negative n, or divide by yn, and this would cancel. Okay, so you end up with this. But now, what is this here is equal to y 1 minus n? Well, that's just u, okay? And so we just got our transformed equation. This has dependent variable u and independent variable x. It doesn't have a y anywhere, okay? And we kind of did this like, you know, without solving for y and then taking derivatives, because, you know, who wants to work with a root, right? It's easier to just work this way. And it works either way. So this is how the transformed equation looks like, and something to note about it is it's linear. So we're in the domain of equations that we do know how to solve. We saw with the homogeneous equations, we were able to transform them to separable ones and solve them. And now we just saw with Bernoulli's equation, we're able to transform it into a linear one. All right, so let's look at an example. Here we have the differential equation that we see here. Not quite in Bernoulli's, Bernoulli's equation, right? We have something in front of the dy in this equation, but, well, let's not let that deter us. We divide by x, noting here that we're going to have to exclude points where x equals 0. And now this is in the form of Bernoulli's equation. And notice here that y is raised to a power 2, so this is Bernoulli's equation with n equals 2. And we're going to choose u is equal to y to the 1 minus n. N here is 2, so we'll put in 2 there. And so you get 1 over y, that's what u is. And so du dx, take the derivative, so y to the negative 1, the negative 1 drops, you get y squared. Don't forget the chain rule, dy dx. And then solve for, why do we do that? Why do we take the derivative with respect to x of u? It's so we could solve for dy dx and make the substitution. So here we solve for dy dx. Now, we're going to get rid of all y's, okay? And so this y here, we're going to, y is equal to 1 over u, so we're going to substitute for y 1 over u. And now we just have a dy on the left-hand side purely in terms of du dx and u. And we're going to take dy dx and we're going to take dy dx and substitute it back into the equation, and this is what we'll get when we substitute it in. And we have a y here. We're going to substitute 1 over u for it. We had a y here, substitute 1 over u. And now we have an equation that's purely in terms of u and x. And this is a linear equation, as promised. And so the integrating factor is going to be equal to the exponential of the integral of p of x. Here, p of x is negative 1 over x. You could review linear equations to see, to go into more depth with this. And so our integrating factor is 1 over x. So then we have the left-hand side now being the derivative of a product, okay? And the right-hand side being mu x times f of x, okay, for linear equations. And so we have this relation. This is what we want. This is why we use the integrating factor for linear equations. Now we integrate both sides. And we end up, it's easy to take the integral of a derivative, so you have that. It's just the product that we were seeking. And integrating, these x's are going to cancel, so you get negative x plus c. And so you solve for u, okay? Are we done? Well, the original problem is in terms of y, so we're not done. Now we have to substitute back. Now, what is u? U is 1 over y, okay? And so instead of a u there, we have a 1 over y, and we take the reciprocal, and now we have y. And this is precisely how these problems are solved, Bernoulli's equation. So it was a different substitution, but it helped us. And substitutions are not just, one type of substitution for all problems. It's kind of like substitution for integration, but there are more kind of recurring patterns here. So let's look at another type of substitution. So if we have a differential equation that's a function of ax plus by plus c, where b does not equal 0 and a and c are any real numbers, well, we could then use this substitution. We take the derivative with respect to x. We get a plus b dy dx. Again, y is always seen as depending on x, and the derivative of c, that's a constant, is 0. And so we get dy dx is equal to the right-hand side there. Plug that into the original equation, right? And you have that for dy dx is now equal to fu, because we made the substitution. And you have this differential equation that is easier to solve. In fact, this right here is separable there, okay? So let's look at an example of doing this. So we have this differential equation. We have the initial value problem, y of 0 equals 0, and we want to solve this. Notice that, in normal form, the right-hand side does have the form ax plus by plus c, where a here is going to be negative 2, and b is going to be 1, and c is equal to 0, okay? So let's make that a little clearer. A is equal to negative 2, b is equal to 1, and c equals 0. So it does have that form, okay? And otherwise, this would have been complicated to solve in other ways. So this is a pretty good method there. You might have tried other ways, but this is the most straightforward. And we take the derivative with respect to x. We get our dy dx. And we then solve for, dy dx. It's going to be, what is dy dx? It's going to be du dx plus 2. We plug it in there, and that's where you're getting this. And on the right, we had, this is u. This was the substitution that we made. So you get u squared minus 7. Move that 2 to the other side, you get minus 9. And now we could separate and integrate. Using, for the u squared minus 9, we do partial fraction decomposition. I have a video in the Calculus 2 playlist for partial fraction decomposition. But you could break up, you could simplify this integral with this expression by using partial fraction decomposition and getting this expression and integrating. And then straightforward algebra gives you that u is equal to this. We're not done, because we have to now substitute back into y. So u is equal to negative 2x plus y. So substitute that for u, and then you just you'll have negative 2x plus y. Move the 2x to the other side, and you get exactly that expression there. This is an initial value problem, so we have the initial condition right here. And on the right hand side, we're going to plug in x equals 0 in our solution. So this gives you what to put in the right, and this gives you what to put on the left. And then you could just solve for c. C is -1, and we are done with the problem, the initial value problem. Okay, and the final type of substitutions we'll look at are equations of this form. And don't be confused, that is not the same as what we looked at above, okay? It's not the same thing, because here, if you solve for dy dx, you have different coefficients, okay? If a2 and a1 were equal, b2 and b1 were equal, then yes, this would work, but they're not, right? So these you have 6 different coefficients here, okay? So it's not the same thing, and so we are in different territory. Nevertheless, let's break this up into cases. So case b1 equals a2. Well, if b1 equals a2, then the differential equation is exact. Why? You take partial m partial y, and you get yourself b1. You take partial n partial x, and you get yourself a2. And if a2 and b1 are equal, this is an exact equation, and we just solve it using the exact equations study that we've done. You could take a look at a video for that. What about if a1 b2 equals a2 b1? Now, I told you that the problem above, why it's not of the same form that we had above, is because the coefficients are different. But if this holds true, then another way to write this, the differential equation, we can put it in the form above, because another way to write this condition is that a2 over a1, b2 over b1, you just divide by b1, you divide by a1, and they're equal. And you just call that, the ratio that they're equal to, just call it k, okay? Just for the sake of presentation. And so here's our differential equation when we put it in normal form instead of differential form. And now for a2, right, this also means here that a2 equals k a1 and b2 equals k b1, okay? Well, plug those in. For a2, plug in k a1. For b2, plug in k b1. And factor out that k. And look, you now have this expression here. And this is the... Now, these two in the square brackets are the same expression. And so you can write this as in the form that we have above, the f ax plus by, where in this case we'll have c equals 0 because we can't add that in there. And that's fine. You just do the substitution similar to what we've done above, and we would be done. Now, what if, you don't have, it's not exact, so you don't have that relation satisfied, and you don't have that relation satisfied, so you could solve it in the form that you have above. So the case where it's not exact and you can't put it as we've done in the case above. Well, all right. Notice that if C1 and C2 were both 0, just for the sake of argument, then the differential equation would look like this. And what we could then do is factor out an x from the top and bottom. If we factor out an x in top and bottom, then the x's would cancel. You'll have just a 1 here. And you'll be left with this expression. And this is a homogeneous equation, okay? In this case, it would be a homogeneous equation. Remember, we said homogeneous equations only depend on y over x. You could have also done this by looking at it as a homogeneous, by looking at m and n as a homogeneous functions. It's clearly homogeneous functions of degree 1. And so, these are equivalent. And so this is a homogeneous equation. So, but that's only true when C1 and C2 equals 0. So that's not going to help us in too much in the general case, but it motivates us. It motivates us to perhaps transform the coefficients of dx and dy into a form that looks like this. Okay, we're going to transform them. This is how our transformation. This is what the end result of our transformation will be. Now, we have these C1s and we have C1 and C2 there that's preventing us. And this seems like a translation problem, okay? So if we choose x to be u plus h, we're going to translate x, and y to be v plus k. We're going to translate y by k, okay? Hopefully these two translations would allow us to have our coefficients now in terms of u and v without the c, okay? Because this is just kind of like this extra term, right? It raises the plane in a sense, okay? And so hopefully we could translate x and y and shift down these expressions to a uv, where the uv axis, this plane would cross the origin, whereas here, it doesn't. So, okay, we're gonna change this into we're gonna translate both variables. And now, of course, the key here is, well, what is h and k? U and v will solve with the differential equation, but h and k, what are those? Well, that's what we got to solve for. And again, look at the end result. So for x, I'm going to plug u plus h. For y, I'm going to plug v plus k. And I'll have my c1. And that's the top equation there. And the bottom equation, we do the same thing for x, u plus h. For y, v plus k. And we have these c1, c2. And we want, our aspiration is to get it in this form. And so what you could do is just distribute the A1s, distribute B1, distribute all these coefficients, and you'll see that, A1U will cancel with this A1U, okay? B1V will cancel with this B1V, and you'll be left with this. And you do the same thing for the second equation, you're left with this. And now you're left with a system of algebraic equations, okay? So this is a system of linear equations. And you have two equations, two unknowns. You're not expected to kind of have a grasp on linear algebra, but if you do, that's a help. This system of linear equations can be written this way, okay? And we know that this has a unique solution whenever A1B2 does not equal A2B1, which is exactly the case we're looking at. Because if this was true, then we can just write it in the form of the case above, okay? And so we already know that that's the case. Otherwise, we would have looked at the previous. And so the previous case. So now we would solve for h and k. Would invert this matrix, or you don't have to invert the matrix. You could just, solve a system of equations. You plug one, you solve for one, you plug it into the other, and then, you just solve in that long way. And notice here that dx equals du, you just take the derivative. This is a constant. H and k are constants. And dy equals dv. And so now the transformed equation, assuming you could do this and solve for h and k, it looks like this. Okay, and that's what we want. And this is homogeneous, and so we would be able to solve it. Let's look at transforming this differential equation here. So for this differential equation, we see that the coefficients are different, but it is of the form that we see here with linear coefficients, okay? And we'd want to transform this to a homogeneous equation. Once we transform it to a homogeneous equation, then we could just look at how to solve homogeneous equations as we've done above. But let's transform this to homogeneous. First, notice that it's not exact. Okay, so we have the situation where B1 does not equal A2. Okay, so B1 there does not equal A2 here. Okay, it's not exact. We also have that A1 B2 is equal to -6 does not equal -2, which is equal to A2 B1. So it's not of the form, it's not this case up here. And so we got to go down to this case. Okay, so we're going to transform x to u plus h and y to v plus k. And we have this equation here. We just we'll have C1, for example, is going to be -6 there, but we move it to the other side, that you'll have a -C1, so it's 6. And likewise, just following this general form there and identifying, A1, B1, C1, you'll get this system of equations. You could solve this system of equations. You don't need a matrix. For example, you could solve for h here from this equation, then plug it in there and solve for k. And you'll get k is equal to -1. And then once you have k is equal to -1, you could say, -3 times -1 is going to be 3. Move it to the other side, and h equals 2. So we got our h and k, and so x is then equal to u plus 2, and y is equal to v minus 1. And this transforms this differential equation into the form that we sought, right? Which is this, which has A1. A1 is what? 2 times u, plus B1. B1 is what? -2 times v, but du here, okay? And u minus 3v, doing the same similar thing here with A2 and B2, dv, and this is homogeneous now, okay? And so you would just solve it exactly like you would solve homogeneous equations, except don't forget that you'll solve for u. U is equal to x minus 2, and so in your implicit solution, you would plug back for u, you would plug in x minus 2, and for v, you'd plug in y plus 1, and then you would have the solution curve.